Hello students, welcome back to Rasayan. In my last video, I have explained introduction and conditions of resonance. In this video, first I am going to explain method of writing resonating structure, or you can say characteristics of resonance. For this molecule, you see double bond, single bond, lone pair, all those are in conjugation. So what will happen? This will transfer electron density in this direction, and here lone pair of electrons are transferred towards pi bond. So what is the resonating structure? Next resonating structure, it is this one. Here this electron density shifted, this lone pair will form double bond here, and if you calculate formal charge, plus it is coming. Here also you can calculate formal charge, or you can use your concept. So you can see in every resonating structures we are showing bonds, covalent bonds, lone pair of electrons, and formal charges were required. So it is written all the resonating structures must be written according to the Lewis method, showing bonds, lone pair of electrons, formal charges were required. Everything you have to show. This is rule number 1. Now see, when we are writing resonating structure, you can observe that there is only shifting of pi electrons or shifting of lone pair of electrons is taking place. But there is no migration of atom is taking place. The position of the atomic nucleus must be unaltered. We have seen for tautomerism there is migration of atom, but in resonance, while writing the resonating structures, your atomic nuclei position will not be changed. Only we are shifting, or we are transferring the electron density, or displacement of electron density is taking place. So according to rule 2, in resonance there is only displacement or shifting of pi electrons or movement of pi electrons or lone pair of electrons. The position of the atomic nuclei of the species must remain unchanged. Means here see, with oxygen hydrogen is bonded, and with this oxygen carbon is bonded. Same thing is happening here. Position of atomic nuclei unchanged. Now see the next rule. What we are doing here, pi bond is converted into lone pair, or lone pair of electrons are converted into pi bond. You have to remember this thing. In resonance, only pi bonds can be converted to lone pair of electrons, and vice versa. 1 2 3 4, 1 2 3 4, 1 2 3, and something is removed, that's why radical. So here this one. This is next resonating structure. Now see, in this resonating structure, one unpaired electron is there, one odd electron is there. Here also another resonate. This is another resonating structure. Here one odd electron is there, or unpaired electron is there. So the number of unpaired electrons in each of the resonating structures must be same. Here one, like this way. Next rule, resonating structures must have almost similar or nearly similar energies. So it is written the several resonating structures must be of comparable energies. Now for the next point, we have studied for resonance of benzene that the sigma skeleton of benzene lie on a plane. Therefore, pz orbitals of benzene with one electron each, they are parallel to each other, and overlap is possible like this way, and pi bond is forming like that way. If overlapping is taking place here, here and here, we will get another resonating structure. But anything which can hamper this planarity in the structure will affect resonance, because then maximum overlap of p orbitals are not possible. So all atoms involved in resonance must lie on the same plane or nearly on the same plane. Any change in the structure which prevents planarity will hamper resonance, because maximum overlap of p orbitals can't be possible to form pi bond. If two adjacent p orbitals, one is like this way, another is like this way, so there is overlapping is hampered. So pi bond formation is not possible, resonance is not possible. So these are the rules, or these are the method of writing resonating structures. Now we will study rules for stability of resonating structures. Suppose we are writing the resonating structures of carbon dioxide. We know all the resonating structures must be written according to the Lewis method, showing bonds, lone pairs and formal charge were required. So this is one Lewis structure of carbon dioxide. It is written resonating structures with more number of covalent bonds are more stable. Now see, if clip this pi bond in this direction, what will be the next resonating structure? This part is intact. Here we are shifting these pi electrons on oxygen. So here we can write this negative charge, formal charge. This is resonating structure number 1. This is 2. And here we will get positive charge, since electron density shifted in this direction, because oxygen is more electronegative. Similarly, what we can do, we can clip this bond. So here this part will be intact. Here we can show this one and plus charge. Now see here how many covalent bonds are there in this structure. 1, 2, 3. Here 3 covalent bonds. Here 4 covalent bonds. So which resonating structure is more stable? This one. Because here number of covalent bonds are maximum. Here covalent bonds are 4. Here 3. Here 3. So here since number of covalent bonds are maximum, so this structure is the most stable, because to bond formation potential energy is released and structure become more stable. Now see, for next rule, this is structure of carbon dioxide and this is one of the resonating structures. Okay. Now see here, carbon is electron deficient. So here oxygen is having lone pair. So it can donate the lone pair here. So what will be the next resonating structure? We can write this part as it is. We are not disturbing this part. Here this lone pair of electrons are transferred here. So what is happening here? We are getting extra pi bond. And since oxygen is losing, actually it is losing one electron, because one electron it is giving to that carbon and another electron it is using for this pi bond. So actually it is losing one electron, so one positive charge, or you can calculate formal charge here. Similarly, what you can do, this is structure number 4. In continuation to this, we are writing this one, giving this number. Or similarly, what we can do, from here it can also give electron density here, transfer electron density here. We can write this one. Now see here, number of covalent bonds are 4, here number of covalent bonds are 4, here number of covalent bonds are 4. So same number of covalent bonds are there in each resonating structure. So it is written, if in the resonating structure same number of covalent bonds are present, then uncharged structure is most stable one. That means this structure is most stable one, since no charge is there, it is uncharged. Here charges are present. Now next point, structure with isolated unlike charges have less stability than those in which they are close to each other. Now see here, opposite charges are close to each other in structure 2 and 3, but here opposite charges means unlike charges are separated. So it is written structures with isolated unlike charges. These are isolated unlike charges. These are having less stability than those in which they are close to each other. Means structure 2 and structure 3 are more stable than 4 and this is 5. Okay. 4 and 5 stability order. So these are 2 and 3 are more contributing to the hybrid than 4 and 5. Because the more the stability of the resonating structure, the more will be its contribution towards resonance hybrid. Now, when we are writing the resonating structures of carbon dioxide, suppose we are cleaving this pi bond. So, if when we are cleaving this pi bond, what is happening here? This part and here, this thing we are getting. And if we are also cleaving this, what will happen? Here also we will get this one and plus. So, here same charges are crowded together. Structures with like formal charges crowded together have very less stability. These are having very less stability. These are not resonating structure of carbon dioxide. These are not resonating structure of carbon dioxide. They are having very less stability. For next we will see, suppose you are having this species. Okay. Now here negative charge, single bond, pi bond, it is present like this way. So what will happen between carbon oxygen? Oxygen is more electronegative, so it will transfer pi electron density here. This carbon will become more electron deficient, so here electron density will be supplied here. So what is the resonating structure here? CH3, CO, here two lone pairs are there and one extra lone pair is coming due to transfer of this pi electron on oxygen. So here we are giving negative charge, formal charge negative. Okay. Now here pi bond CH2. This is structure number 2. Now see here, between structure 1 and structure 2, which one is more stable? Oxygen is more electronegative and carbon is less electronegative. So on oxygen atom, negative charge is more stable, but on carbon atom, negative charge is not that much stable. So between 1 and 2, which one is stable? 2 is more stable than 1. Once again I am telling, negative charge on more electronegative atom is more stable. Positive charge on less electronegative atom is more stable, but here negative charge is there on less electronegative carbon atom. So this is not that much stable. So if you compare the stability between these two, this is more stable than this. Suppose you are having these species, lone pair, single bond, double bond, vacant orbital, it is there. So here resonance is possible. Now see, this carbon is having how many electrons? This carbon is having 6 electrons. Because here one extra hydrogen is there. So 1, 2, 3, 4, 5, 6. 6 electrons are there. So incomplete octet is present there. Now we have to show resonance. This pi electron density will be transferred here and here lone pair will be transferred here. So what will be the resonating structure? Formal charge here positive. Now see here 1, 2, 3, 4, 5, 6, 7, 8. This atom is having, bromine atom is having 8 electrons. Here one hydrogen is there. You have to satisfy the valency of carbon. So 1, 2, 3, 4, 5, 6 and here one hydrogen is there. 7, 8. So it is having 8 electrons. It is also having 8 electrons. All other carbons are having 8 electrons in its valence shell. So octet is completed here. So if this is 1, this is 2, which one is more stable? 2 is more stable than 1, because the resonating structure with complete octet at each atom is more stable. Next rule, equivalent resonating structures gives large resonance stabilization. Now consider about carbonate ion. This is carbonate. We will draw resonating structure of carbonate ion. Carbon is bonded with one oxygen with one double bond, and carbon is bonded with two oxygen atoms, and these are having one negative charge. If you calculate formal charge, it is coming negative, because here see, formal charge, oxygen is having 6 valence electrons, 6 lone pair electrons, and one bond pair. So totally it is coming -1. Now from here, how to draw the next resonating structure? Oxygen is more electronegative. We have to shift these pi electrons on the oxygen, and carbon will become electron deficient. So this electron density, lone pair of electrons, will be transferred here to make pi bond. So what is the next resonating structure? This one as it is. Here 2 lone pairs, these pi bond electrons are transferred here. So here negative charge, it is coming as lone pair, extra lone pair, and here carbon oxygen double bond. Here also we can draw the next resonating structure. We can break this bond and it can come here. So here now carbon oxygen double bond, here this and this. So you can see these three structures are equivalent. So it is called equivalent resonating structures. If system is like that, it is having equivalent resonating structure, it gives large resonance stabilization for that species, and these have same energy. Now what is the resonance hybrid of the carbonate ion? Basic skeleton you write. Here double bond is there, here carbon oxygen double bond is there, here carbon oxygen double bond is there. So one broken bond in each case we have to show, and here partial negative charge is there. Here negative charge, here negative charge, here negative charge, it is there. So this is resonance hybrid. Or you can show this resonance hybrid like this way: carbon, oxygen, dotted bond, and total 2 charges, it will be divided by 3, means -2 by 3, -2 by 3, -2 by 3. Each resonating structure should have same charge. So here -2, here -2, here -2, and resonance hybrid also it is containing -2 by 3 into 3 means -2. Partial negative charge. So energy wise, if this is 1, this is 2, this is 3, all the 3 are having same energies. So they are equally contributing, and this type of equivalent resonance gives much more stability to the species. For acetate ion means from acetic acid, by removal of H plus, we will get acetate ion. So this is the Lewis structure of acetate ion. Here also equivalent resonance you can observe, and For that reason, this and this are having equal energy and it gives large resonance stabilization to that species. In this video, till that, resonance will be continued in the next video.